Here we got a circuit with two supply voltages. We have a left supply voltage of 12 volts and an internal resistance of 2 ohm. The right supply voltage is 9 volts and an internal resistance of 1 ohm. Then we also have three resistors in a circuit. The left one is 5 ohm, the middle one is 7 ohm, and the right one is 3 ohm. Up here we measure the current in the right branch, and it is 0.40 amp. We want to calculate the current in all the system. To the left side we have a current over here. We call that current number 1. In the middle we have a current. We call it current number 2. And to the right we have a current over here. We call it current number 3. Many times we think that for calculating the current over here, we just have to take the voltage, 9 volt, divided by the total resistance in this closed loop. The total resistance is 1 ohm in serial with 3 ohm and 7 ohm. So we have a total resistance of 11 ohm. So we can calculate the current by taking the 9 voltage and then divide by the total resistance of 11 ohm. And the calculator said then you should have a current of 0.818 amps. We can see over here that actually the current is 0.40 amp, so this calculation is wrong. It's because that we have a supply system over here, and it also generates a current this way around, and the current for the middle resistor is then higher and has then influence of the current over here. So when you have more than one supply system, we normally not can use Ohm's law to find out the current in all the system. Then we're going to use another law, and that is Kirchhoff's first and second laws. The first law is regarding current in a connecting point, which current is going to the connecting point and which current is going from the connection point. Actually here we can see it because we have these circles. It is the electrons. So actually over here on the left side the electrons going down, but the current will then go up and to the right. Over here the current go up and to the left, and in the middle the current go down. The reverse way of the electrons. That's also normal because we have the positive side of the battery here, so we think that the current will go this way, and the positive side of this battery, so the current will go this way. But it is also depend on the size of the resistors and the voltage for both batteries. For example, over here, if we change the voltage to a lower voltage, we can make that the current will flow the other way. For example, we can change the voltage to a 4 volt. Then we can see that the electrons goes the other way. So right now the current goes down and charge the battery. So right now this battery is charged and this battery over here is discharged. But we'll switch to 9 volt again, so we get the situation from before. So now both batteries are discharged. Kirchhoff's first law was about the current to a connection point and the current from a connection point. Kirchhoff's second law is about the voltage in a closed loop, and the supply voltage must be equal to the voltage drop across all the resistors in a circuit or in a closed loop. But we'll start with Kirchhoff's first law, And up here we can make an equation from the current I1, I2 and I3. Down here we also have a connection point, but it is the same story because you have the current I1, I2 and I3. So we only have to describe one of these connection points. Kirchhoff said that the current which go to the connection point must be equal to the current which go away from the connection point. So right here, current number 1 goes to the connection point, current number 3 goes to the connection point, and current number 2 goes from the connection point. Or you can also say that the current which goes to the connection point is positive and the currents which go from the connection point is negative. We'll try to make some equations so we can find out the values for the current I1, I2 and I3. Kirchhoff's first law said that I1 plus I3 minus I2 is equal to 0. That was when we have the thought that the current which go to the connection point is positive and a current which go away from the connection point is negative. We also can make the formula that we said that I1 plus I3 is equal to I2. So the current which go to the connection point is equal to the current which go from the connection point. But if you move I2 over on the other side of the equation sign, we got the formula down here. This one is better to use when we have to use it in solving a matrix system, so that we have the current of one side of the equation sign and a value on the other side. We cannot make any more equation with Kirchhoff's first law because this connection point describes the same story. So we have to make some equation for Kirchhoff's second law. And the second law said that if we have a closed loop, for example, on the left side, then the generated 12 volts from electromotive force in this battery must be equal to the voltage drop across all the resistors. We have an internal resistor in a battery, and the current I1 flows through this resistor, and I1 also flows through this resistor up here, but over here it is I2 which flows through this resistor. We call this resistor R1 and the internal resistor I1, I for internal, and over here we have R2. Here we have R3 and internal resistor I3. So we're going to make the equation for this closed loop on the left side. We have that A1, that was the electromotive force in a closed loop, and that's equal to the voltage drop across all the resistors. First we have the internal resistor RI1, and we should multiply by the current, that was I1. We have to decide if these values is positive or negative. For the electromotive force, we go from negative to positive. It means that here we go in a positive direction, and then E1 should be positive. On the other side of the equation sign with all the voltage drop across the resistors, we have that if we go the same way that the current flows, or we guess that the current flows, then the value should be positive. And on the left side, if we go clockwise, we follow the current both over here, I2, and here for I1. So all the values for the voltage drop should be positive. So it must be plus, then R1 times I1. You can just copy this one and change it to R1 times I1, and then plus R2 times I2. So we can see here that actually I1 is multiplied with RI1 and R1 both places, so we can make this equation a little bit more simple. So it must be equal to RI1 plus R1 multiplied by I1. So R1 and I1, put it into a bracket, so we make this part more simple. And then plus R2 times I2. Now I can put in the known numbers. We have the number for the electromotive force and the numbers for all the resistors. E1, it was 12.0 volts. That's equal to, and then we just copy this one and put in the values for the resistors. The internal resistor for the supply in the left side is 2.0 ohm. R1 is 5 ohm and R2 is 7 ohm. So gives us that we have 7 I1 plus 7 I2. So we have 12 is equal to 7 I1 plus 7 I2. So now we have two equations, but we remember that we have 3 unknown currents, so we have to make another equation, and we can do that with Kirchhoff's second law. It will be easy to just make a closed loop on the right side, but that will be nearby the same formula as before, just with some other values. So I decide that we have to take the outer loop so that we have 2 electromotive force in a loop. So we take this loop and we are going clockwise, and over here we go the same way as the current, so the voltage drop across these 2 resistors must be positive, but over here we go in the opposite direction of the current, so the voltage drop across these 2 resistors must be negative. For the voltage, here we go from negative to positive, so this one is positive, but over here we go from positive to negative, so this one must be negative. We make the equation and set that all the voltage in a system, all the supply voltage, that is E1, and then we go from positive to negative, and it's minus E3. That must be equal to, and then all the voltage drop. Over here we have the same story as before, so we just copy that. Then it is minus R3 times I3. And then again minus RI3 for internal times I3. RI internal 3 times I3. Again, we can make it more simple because I1 is multiplied both sides here, and I3 have also been multiplied by RI1, RI3 and R3. So we can say that it must be the same in the first sub here, and then minus. These two parts are negative, so it must be in the minus, and then it must be R3 plus R internal 3 times I3. We will now put in the numbers. E1 was 12.0 minus E3 was 9.0. That gives 3.0. That is also equal to this formula. Copy this one and put in the numbers for all the resistors. The internal for the left side is 2.0 and R1 is still 5 ohm. R3 is 3 ohm and internal RI3 is 1 ohm. It gives that we have 7I1 and minus 4I3. Then we have 1, 2, 3 equations, and that is enough to solve the system. We can do it manually, but I think we're going to use matrix system to solve the 3 unknown current. This row is for current I1, this row is for current I2, and this one is for current I3. So I1 and I2 and I3. Here we have the numbers for the current, and here we have the result. The first line said that if we take 1 I1, 1 I3 and negative 1 I2, we get 0. So we have to put in 0 out here, that's the result. And we have 1 I1, we have negative 1 I2, and we have 1 I3. The next line is for the next equation. The result was 12, and we got 12 if we take 7 I1 and positive 7 I2. So here we have to put in 7 and 7 and 0 for I3. The last equation, we have the result is 3, and we got 3 if we take 7 I1 and negative 4 I3. So gives 0 I2 and negative 4. So now we have the matrix system. This is the A matrix, 9 numbers. This is the B matrix, 3 numbers. And the X matrix is the result we can put in down here if you want that. We use the calculator and we enter the numerical solver and we choose solve linear system. Then we have the A, B and X matrix. We edit the A matrix and in this column we have to put in these numbers 177, but I have set it up for going to the right, so we start up with this line 1, -1 and 1. So 1, enter. 1, it should be negative, so plus minus, enter, and 1, enter. The calculator doesn't know that we only have 3 unknowns, so the first time we just have to move the cursor down here. Then the next line is 770. We key in a number 7, enter, 7, enter, and 0, enter. Then finally we have 7, 0 and -4. Key in the numbers 7, enter, 0, enter, and 4 plus minus, enter. Then we have entered the A matrix and we press enter again just to exit A matrix. Use the arrow to go down to B matrix and edit B matrix. We have the numbers 0, 12 and 3 to put in the B matrix. They has to be in the same column, so we just key in 0, enter, and again use the arrow to go down to the left, and 12, enter, and 3, enter. That's the B matrix. We press enter again to exit the B matrix and go down to the X matrix and press solve. We can press enter to get the 3 values, and we can see up here that's the value for current number 1, current number 2 and current number 3. We can see it is 0.4 amp, and if we go over here, yes, it is 0.40 amp. Current I2, the meter set is 1.06 amp. Calculator set 1.0. Yeah, it is 6 if we make it to 3 significant numbers. And up here, current number 1 is 0.66 amp. Yes, correct. If we want to store this in the variables, we just have to remove these brackets. So we enter program, PRG, left shift K and N for enter program. Press F5 for type, F1 for object. Then we have to delete solutions. Press F1 again for object. Delete this line. It is a 3-1 matrix. And then we got the numbers for the current. And we enter the variable. And we can store. The lower one is current I3. We store that in number 3. And current number 2, start in number 2, and current number 1, we start in number 1. And then we have the current if we want to make any calculation. So that's how we can calculate the current in a circuit where we have 2 or more supply systems and we are using Kirchhoff's law.